my name is Sarah. I'm a junior studying computer science on the artificial intelligence track at Stanford.
And hey, my name is Umar. I'm a senior at Stanford University studying computer science, also on the artificial intelligence track. And this is our presentation, Predicting Bazel Build Times Using Machine Learning.
So let's start by discussing why we chose to do our project on this topic. Well, our first and most direct goal was increasing engineer productivity. So, a lot of you guys are engineers, and so you'll understand that when you start building your code, you frequently take a coffee break. Sometimes you even start another coding project. But how do you know which one of those things to do? Well, that's dependent on how long the build will take. So by predicting Bazel build times, we allow you guys to be better able to allot your time as you see fit. Our long-term goal is to decrease energy consumption. And the way that predicting Bazel build times relates to this is that by predicting times, we can kind of flag which builds are the most problematic or the longest builds. And then we can focus in on those builds, hypertuning parameters such as the jobs flag, and trying to make sure that we can make those build times specifically more optimal in general, decreasing energy consumption over time. So now we're going to talk a little bit about the data we fed into the algorithm. So our data set came from the Bazel project on GitHub. And the reason we chose the Bazel project is that each Bazel build has a build event protocol, which allows us to be able to get the CPU time it took for the build to happen, which is exactly what our output data is. In general, we took 500 commits from this GitHub repo. The reason we chose 500 is a constraint on our part of time as well as our computers. It took us about a whole day just to pull 500 commits. And then the way we spread out those commits was 300 training commits, 100 validation commits, and 100 testing commits.
So why did we choose commits to Bazel as our data set? Well, our goal was to understand where changes in the code base affected build time. And to best understand that, we wanted to see in each commit which changes were made to affect the build time that was found in the build event protocol of each build. And further diving deeper into why we chose certain features within each commit, well, we wanted to understand what changes were made. And that kind of broke down into two different choices. Did we want to look at which files were changed, or do we want to look at what code itself was changed and how much of it was changed? We decided to go with file path with the understanding that 100 lines of code changed in a file like source main is much more impactful based on file dependencies than, say, 100 lines of code changed in third party. And for that reason, our goal was to relook at the file path changed and understand where in the code base those changes were made to affect the build time. And so that leads us into our input data, which was we took each file path within each commit to Bazel and we broke it down into pieces. And the pieces that we chose to break it down into were the prefix of the file and the file type at the end. And what we did was that for each file path that was changed within each commit, we took the prefix, for example, source main, examples, scripts, third party. We took the file type, for example, C, C++, HTML, and we aggregated that data to understand which file prefix was the most common prefix changed and which file type was the most common file type changed within that commit. And then our next step to pre-process that data for our linear model, or our machine learning model, I should say, is to put them into TensorFlow categorical columns. Similarly, for our output data, we obtain the build event protocol for each commit. This harps back to why we chose to work with Bazel in the first place, is that it gave us access to this very clear output data of the exact build time that was within the timing metrics of each build event protocol. And based on the CPU time of each build, we were able to understand exactly how long each build took based on the file type and the file prefix that was changed for that commit. And so using this data, we were able to start thinking about our machine learning model and exactly which model we wanted to pick. The first thing that we had to decide was whether we were going to work with a supervised learning model or an unsupervised learning model. What we understood about the supervised learning models was that they took in very explicit labeled input and output data. And what that allowed one to do is that you can get very clear accuracy because you understand exactly what you're looking for. There are very explicit results that you can say that if this is the build time, we are exactly 5 seconds with our prediction off of what the exact build time should be. On the other hand, with unsupervised learning, you don't need that labeled input and output data because the goal is to find patterns and clusters of data within that raw data. And for that reason, it was very clear for us, because we had access to very explicit input and output data, to go with a machine learning model, and more specifically, a linear regression model.
So the algorithm we ended up selecting was linear regression, which is a supervised learning algorithm. And these are the main parameters for linear regression. So the two most important parameters on this slide are learning rate and batch size. So too low of a learning rate means that the algorithm's training will progress very slowly, and as a result, you may not be able to account for all of the data, or you'll end up waiting way, way too long for the algorithm to train. Too high of a learning rate means that the model will converge too quickly to a suboptimal solution, and it won't account for all of the nuances in the data. And then batch size relates to learning rate. There are ideal batch sizes for learning rates. So we wanted to make sure that we got the ideal learning rate batch size combination, because having that ideal combination would keep us from having issues such as overfitting. And so there was a lot of guess and check involved in point one and 16. Other than that, you see the optimizer on the slide. So our current optimizer we chose to use was SGD. That's a very commonly used optimizer. Its only real drawback is that if you have a lot of data, it can be pretty slow, but that wasn't a problem we encountered. Our metric for accuracy was root mean squared error. And so um, we knew that the lower this value, the better we're doing. And finally, an additional kind of layer we added to linear regression was feature crossing. So walking into this project, we had no way of knowing if the relationship between file type slash prefix and CPU time is linear, or whether it's exponential or anything else. And so by doing feature crossing, we were able to use a linear regression model to make predictions for a relationship that was potentially not linear. Um, yeah. So now digging a little bit into what our actual results were. So in terms of accuracy, you guys see two different graphs before you. One is with feature crossing, one is without. And there's a couple things that I really want to highlight here. The first is that you see that the training and validation data lines are about the same, and that is a very good thing. If there was a significant difference between the two, we would know that there is definitely overfitting in this model. The other thing that you see in both of these graphs is that there's no like kind of sharp, super sharp turns. You know, you don't go from like no error to a lot of error all of a sudden. Any super sharp turns like that would also let us know that there's overfitting. On the converse side, you see that our average error was around 5,600 or 5,700 milliseconds. And that's pretty good as well, because our build times were, you know, anywhere from 10,000 to 50,000 to even 100,000 milliseconds. So that value really tells us that for our bigger builds, which are the ones we really care about, our error is relatively negligible. And then finally, you see that the difference between the error with feature crossing and without feature crossing is not that significant. It's really only 100 milliseconds. And that tells us that the relationship between file type slash prefix and CPU time likely is linear.
So taking a step back, what this means for our model accuracy is that we can predict Bazel build times with a 6-second margin of error. That is very significant because for builds that take longer than 1 minute, 2 minutes, 5 minutes, 30 minutes, an hour, it is very, very useful for the engineer to understand that when you kick off a build, within 5 to 6 seconds of error, you'll know that this is going to take X amount of time, and you are free to do whatever you'd like as an engineer with that time, and thus increase your productivity. And this leads us into our next steps, which is kind of like a roadmap for where we see this project going forward. There are two things that we can do to increase the accuracy of our model. The first thing is collecting more data. Due to time and resource constraints, because we had to let every single build run on our local machine and to be able to collect the output data of the build times, we had to let each build run in its entirety, one after the other. We could only collect 500 pieces of data out of almost 30,000 commits to Bazel. So simply taking more time and more resources to collect more data, we will be able to better understand the changes in the code base to Bazel and how that affects the build time. Another thing is increasing the granularity of our data. As I mentioned earlier, we took the file paths that were changed and we broke them down into the prefixes and the file types and further aggregated that into the most common prefix and the most common file type. Rather, what we could do to increase the granularity of our model and better predict build times is we could take in that entire file string with the prefix, the pieces in the middle, and the file type, and also take in every single file path change for every commit to better understand the data. And with those in mind, we can start building towards a more accurate machine learning model to predict Bazel build times, and then further use that model to understand which builds take how long and how we can use that data to further optimize build times and thus work towards our largest goal of decreasing energy consumption. Thank you so much.
So thank you so much for listening to our presentation, and let us know if you have any questions.